IntroVirt is an event-based introspective hypervisor architecture and tool stack. It runs with Xen Server and can introspect Windows and Linux or Unix virtual machines. The IntroVirt tool stack provides users with granular control of VMs from the application level all the way down to the system call level. This granularity of control can be leveraged to provide asset protection, access control, user interface manipulation, automated testing or training, behavior analysis, and much more. The IntroVirt architecture is shown here. Starting at the bottom, we have the hardware layer, followed by the hypervisor layer where Xen Server runs. Above the hypervisor layer, we have the IntroVirt hypervisor hooks. The hooks patch the functionality of Xen to allow IntroVirt to receive guest virtual machine events. On the top right, we have the guest virtual machines. IntroVirt will be monitoring these guest VMs for specific events or activities. When these events or activities occur, control is passed up to the IntroVirt introspection tool stack shown at the top left. At the bottom of the tool stack, the introspection abstraction layer receives events from the guest virtual machine. From there, the event is passed to the operating system layer, where it is used to parse operating system-specific structures and system calls. Finally, control is passed to the introspection application layer, where individual introspection applications can view or modify guest virtual machine memory, alter function parameters and return codes, or monitor system activity. The introspection application then returns control back to the guest virtual machine and waits for new events. Here we have a Linux machine running Xen with IntroVirt. On the right, we have a Windows 7 guest VM. On the left, we have the IntroVirt tool suite. We will use the tool suite to monitor and modify the behavior of the Windows 7 guest. The first tool we will demonstrate is the System Call Monitor. This tool will display all the system calls occurring in the guest with their arguments and return codes. Using the process filter, we can restrict the output to the system calls originating from a specific process. In this case, we will monitor Notepad. As it opens, you can see activity in the System Call Monitor window. System call monitoring can be used to gather useful information about activity occurring within a guest. Applications of system call monitoring include behavior analysis, reverse engineering, and code analysis. Next, we will demonstrate system call injection by pushing an executable file from the Linux host to the Windows VM and triggering its execution. The file to be pushed is a Windows batch script to launch the calculator program. IntroVirt takes advantage of system call injection by injecting write file system calls until the file is written. Once pushed, we can point the execution tool to the path of the new file and trigger its execution. The execution tool works by injecting the appropriate system calls to start a process. This can be used to execute any file on the system from the hypervisor. Both of these operations are done without the need for a network connection and without guest VM cooperation. System call injection can be used to trigger any operation within guest VMs that can be represented by one or more system calls. Applications of system call injection include application testing, automated training, and user interaction manipulation. Next, we will demonstrate arbitrary memory breakpoints by viewing and modifying the memory used by WinMine to store mine locations. To view the locations of the mines, IntroVirt inserts a breakpoint into the WinMine process that is triggered once the game board is generated. After the breakpoint is triggered, IntroVirt can read the memory for the game board. As you can see, the red squares in the WinMine viewer on the left correspond to the mine locations in the game running within the guest VM. Now we will change the WinMine viewer from monitor to overwrite mode. To modify the game board layout, IntroVirt uses the same breakpoint as before, but overwrites the board in memory to create a custom arrangement of mines. This technique could be leveraged for memory forensics, text box monitoring or modification, and memory protection. Next, we will demonstrate access control by preventing Notepad from opening files with the name block.txt. When we attempt to open the text file with Notepad, IntroVirt intercepts the call to open the file and overrides the return code to be the value of the access denied status. Now we will enable the Terminate Process option in the IntroVirt tool. With this option enabled, IntroVirt will kill the process attempting to read the file. The techniques used by IntroVirt for access control could be applied to build applications that provide data loss prevention or the enforcement of role-based or rule-based access controls. Finally, we will demonstrate asset protection by blocking WinSock for the netcat process to prevent insecure communications. Before we block WinSock with IntroVirt, the guest VM is able to receive messages over the network. Now we will block the WinSock functionality via the IntroVirt tool. Once the block is enabled, Netcat will not be able to listen for or send messages over the network. As you can see, the Netcat process fails because it is unable to call functionality within the WinSock DLL. However, since this block is on a per-process basis, other applications that require socket functionality will continue uninterrupted. Using these techniques, tools could be developed to provide a hypervisor-assisted firewall, traffic monitor, and network-based APT detection or prevention. This video has demonstrated a test drive of IntroVirt's functionality. The IntroVirt architecture provides users with the instruments required to create new tools and extend existing capabilities. Contact the IntroVirt team to arrange for an evaluation copy and begin building your custom IntroVirt applications today.